So now we are going to discuss about thermodynamic and kinetic stability of transition of metal complexes. There are two stabilities. One is thermodynamic stability and kinetic stability. Thermodynamic stability is going to explain about the stability of the complex. Stability of the complex. That means how much stability of the complex, how much long time, how much long time, how much long time the complex is going to stay. That's what thermodynamic stability is going to give. Now kinetic stability is going to give the speed, how much speed the complex is going to, speed of the formation of the complex. This is information is going to get from the kinetic stability. So there are two stabilities, one is thermodynamic stability, other one is kinetic stability. Right. Now moving on to thermodynamic stability. So thermodynamic stability, it is going to measure the amount of complex at equilibrium. For example, at equilibrium, how much compound is going to form? That amount is going to be explained by thermodynamic stability. Now, when the thermodynamic stability product will be more, there are some factors which will give you more amount of thermodynamic product, stable product. That is going to be based on the interaction between metal and ligand. Imagine the metal and ligand forming a complex in which the interaction between metal and ligand is too good. Then the complex which is going to form is going to be stable, that is thermodynamic stable. Because the stronger the interaction between the metal and ligand, more is the stability of the product. More is the thermodynamic stability of the product. Thermodynamic stability. Right. Next factor is going to be the based on equilibrium constant. Greater the value of equilibrium constant, more is the stability of complex, that is thermodynamic stability. Thermodynamic stability will be more if equilibrium constant is more. If equilibrium constant is more, thermodynamic stability is more. If more is interaction, thermodynamic stability is more. So let us see this one with an example based on thermodynamics stability constant. For example, Cu plus 2, this is going to form a complex with 4 ammonia molecules. So it is going to form tetraamine copper 2, tetraamine copper 2 ion. In this one, the stability constant is going to be 4.5 into 10 power 21. The same one, the same type of complex is forming with different ligand, in which 4 cyanide ions are going to form complex with copper and going to produce tetracyano Cu plus 2 ion. Right? In this one, the equilibrium constant is going to be 2.0 into 10 power 27. So where equilibrium constant is more, here is equilibrium constant more. And so this is going to form more thermodynamic stable product. Thermodynamic stable product. We already discussed more is the thermodynamic stable constant, equilibrium constant, more is the thermodynamic stability. So how to understand without looking that K value, how to predict this equilibrium constant will be more. So it is based on the ligand. If you are looking into the ligand, right, ammonia versus cyanide. Cyanide is stronger ligand. Already we know in spectral chemical series we have discussed stronger ligand, and so it is going to form a complex which is stable complex. So stability of this particular one can be easily understandable by looking into the example. Now, which is more stable? Based on the equilibrium constant, this is more stable. How to understand? Whichever is strong ligand, that is going to form more stable complex. Now, looking into this particular thermodynamic stability, the thermodynamic stability can also be, one second, yeah. Next, let us look into the next example in which this is also going to be based on equilibrium constant only, but the ligands are different. One is ammonia, that is a monodentate ligand, and other one is bidentate ligand. Bidentate. What is the meaning of monodentate and bidentate? To this nickel, if lone pair of electrons are donating from only one center, then that is called as monodentate. To this nickel, ethylene diamine, ethylene here this will have two centers to donate to this nickel ion, so it is going to be called as ethylene diamine, going to be called as bidentate ligands. Among this one, which is going to form strong complex or stable complex, the one who is with bidentate ligand. The bidentate ligand is going to form a thermodynamic stable complex that can be understandable from the equilibrium constant, which is 4.6 into 10 power 18, and compared to this with ammonia ligand, it is very high, right? This is thermodynamically stable. Now, why it is thermodynamically stable? Just like the previous case, one is stronger compared to other ligand, right? Here always monodentate ligand compared to monodentate ligand, always bidentate ligand will form more stable complex bidentate ligand. That's what the reason which is giving you thermodynamic stable product, right? So thermodynamic stable product can be explained based on this strong ligand or bidentate ligand in this by using this equilibrium constant. Now looking into this particular thermodynamic stability of complexes can also be understandable from the dissociation constant. Dissociation constant, that is K dissociation, is inversely proportional to dissociation constant is inversely proportional to equilibrium constant. We can write it as K dissociation is equal to, because both are constants, right? We can write it this is equilibrium constant, this is dissociation constant. So if more is a dissociation constant, lesser is a stability, lesser thermodynamic stability, and lesser is the dissociation constant, more stability of more thermodynamic stability of more stability with respect to thermal stability. Lesser stability, more stability. It is based on dissociation constant. Whereas based on equilibrium constant, more is equilibrium constant, more is thermodynamic stability. Lesser is equilibrium constant, lesser is thermodynamic stability. Coming to the dissociation constant, it is inversely proportional, and so more dissociation, lesser stability, lesser dissociation constant, more stability. Now moving on to the next concept, that is stability concept 2, that is kinetic stability. What is the meaning of kinetic stability? We already discussed that kinetic stability is going to give the information about the speed of the reaction, speed of the complex formation. Now it is refers to the speed, that means rate of the reaction with which the transformations leading to equilibriums will occur, right? During equilibrium, which side is going to be fast? That's what is going to give you kinetic stability. So kinetic stability is given in terms of two factors. One is lability, other one is inertness. What is the meaning of lability and inertness? Lability means reactive, most reactive. In one way, it is going to be inertness means non-reactive, right? Reactive and non-reactive. What is reactive and non-reactive? Let us discuss with respect to this kinetic stability. If one metal, if some ligand is there, if this ligand can be replaced with other ligand very fast, then the ligand, for example, it is going to form Ml2 by replacing with L1. Then this L1 is going to be labile. With other ligand, if this ligand can be replaced pretty easily, then this L1 is called as labile. What is the meaning of labile? Reactive. Consider some Ml3 and you are reacting with L4. but it is not reacting. No reaction is occurring. No reaction is occurring. And so here L3 we will call it as inert ligand. What is the meaning of inert and lability here? So overall the process is called as lability and inertness. Here inertness. Lability and inertness is based on the ligand. If for example the ligand attached to the metal, it is reactive, then it is going to be labile ligand and the process is called lability. And if the ligand is not reactive, then it is called as inert and it is called inertness. Based on this lability and inertness, we will explain the kinetic stability. Now, kinetic stability of compounds is different from thermodynamics. There is no relation between this thermodynamic stability and kinetic stability. Both are completely different. And so, in other words, the inertness and lability of complex has nothing to do with the thermodynamics stability. Very important point to be noted. In general, in competitive exams, this type of questions will be given. Is there any relation with the inertness and lability with the thermodynamic stability constant? No. Inertness and lability belongs to kinetic stability but not to thermodynamic stability. Both are completely different. And now we are going to discuss the kinetic stability with an example. For example, if we are considering here one complex, okay, this is going to be stable. That complex ion is found to be kinetically stable, which is kinetically stable. In which medium? Acidic medium. But for a long period. But if you are reacting here, right, it is going to form this type of complex and ammonia molecules are out as ammonium ions. Here the equilibrium constant K 10 power 25 is representing the forward reactions taking place. From this one, what conclusion we can get it? Of course, larger the K value, it is leading to the forward reaction. From this one, what we can understand clearly, this particular complex is stable in kinetic, that is kinetically stable in acidic medium, whereas the same complex is thermodynamically unstable. Here we can see the same reaction here. It means that the complex of the cobalt on the reactant side is inert with respect to kinetic stability. Inert with respect to kinetically. But thermodynamically what happening? It's giving the product, right? So thermodynamically it is unstable in acidic medium and so giving the product. So thermodynamic unstable and kinetic stable, both are not related at all. That's the point to be noted here. And with this we have completed the stability constants based on thermodynamic and kinetic.